Hey everyone, welcome to Professor Calculus's YouTube channel. This video we're gonna see how we should solve this integral that I've prepared for you. Before that, make sure to like and subscribe as this free and you can always change your mind later. So, the trick that I can use here, actually this was supposed to be e to x to the I x, x to the negative, sorry, x to the I x dx. So if you want to find the area under this curve, which is an imaginary curve, a complex number, a complex function, you probably know that we cannot express this function as an elementary antiderivative, so we have to use other techniques. So for that, to begin, I'm going to define I to be e to the power of natural log of x to the ix dx. So you remember that if I say, for example, e to the ln x, it is actually x. So I can raise this whole thing to the power of e to the ln of something and get the same thing. And according to the property of logarithms, I can move this here, or move this ix here. So I can be the integral from 0 to 1 of e to the ix ln x dx. So now, the trick that I'm going to use the Maclaurin series, the series for e to the x, as an infinite sum from 0 to infinity, which is going to be x to the n over n factorial. And if I want to have e to the ix ln x, I'm going to get the sum from 0 to infinity of ix ln x to the power of n over n factorial. Therefore, I can write this integral here from 0 to 1 as the sum. Sorry, let me choose another color. It's the sum from 0 to infinity of 1 I to the x, I to the n, x to the n, and ln x to the n of all over n factorial dx. So the reason that I put these things on different colors is that I want to show to you that we can actually factor these two out of the integral because they're constant with respect to integration. Thus, we can have I equals to the sum, infinite sum from 0 to infinity of I to the power of n, over n factorial. And I'm going to have the integral from 0 to 1 of x to the n ln to the power of nx dx. So here the trick that I'm going to use, I'm going to do a variable substitution here. I'm going to say that t equals to ln x. Thus, when t equals to ln x, I'm going to change my bounds. When t equals to 0, ln x is negative infinity. Negative infinity is positive infinity. Thus, when t equals 0, when x equals 0, t equals infinity. And when x equals 1, t equals 0. Therefore, we can say e to the negative t equals to x, and dx is negative e to the negative t dt. I can do all these substitutions for my integral here. Therefore, I'm going to have the infinite sum from 0 to infinity of I to the n over n factorial, the integral from infinity to 0, x to the power of n is e to the negative t to the power of n. Ln x is negative t to the power of n, and now my dx is negative e to the negative t dt. And if I write this integral more cleanly here, I'm going to have the infinite sum from 0 to infinity of I to the n over n factorial multiplied by a negative sign here, t infinity to 0 of e to the negative tn, negative t to the n, e to the negative t dt. Why did I put the negative sign in red here? Because I wanted to show that we can actually change the bounds of this integral if we multiply it by negative 1. Thus, I equals this now from n equals 0 to infinity of I to the n over n factorial, the integral from 0 to infinity of e to the negative tn, e to the negative t, negative t to the n dt. Now, I can expand this a little bit further, simplify it. The integral from 0 to infinity is gonna sum up. So negative tn minus t times negative t to the n dt. So I'm gonna write it again here. I to the n over n factorial e to the negative t times n plus 1, and I can decompose it as negative 1 to the n. So let me write it in another color because it's constant. Negative 1 to the n and t to the n dt. So I can move this out again, and I'm going to be getting the integral equals the sum from n equals 0 to infinity of negative I to the n over n factorial, the integral from 0 to infinity of e to the negative t times n plus 1 t to the n dt. So hold on, we're very close to the end. I'm going to do another variable substitution here, which is defining u to be equal to t times n plus 1. Therefore, du is dt times n plus 1. We're differentiating both sides here. T here is u over n plus 1. And dt here is du over n plus 1. Thus, I can make a replacement here. Substitution n equals 0 to infinity of negative I to the n over n factorial, the integral from 0 to infinity of e to the negative u. T to the n is u over n plus 1 to the power of n times du over n plus 1. I equals the integral, the sum from 0 to infinity of negative I to the n over n factorial, this thing right here, negative u to the n times du over n plus 1 to the power of n times n plus 1, is going to be n plus 1. And therefore, I can move this again out here. The infinite sum from negative I to the n over n factorial over n plus 1 to the power of n plus 1, the integral from 0 to infinity of e to the negative u to the n du. Well, now this integral has a already defined value, is the pi function, and is equal to n factorial. Therefore, I can suppress, if I write it again here, it's negative I to the n over n factorial n plus 1 to the, times n factorial. I can cancel out these two. Therefore, I'll get my I, the integral from 0 to infinity, to be the negative I to the n over n plus 1 to the n plus 1. And that is the actual value of my integral represented as an infinite sum. So therefore I can say the integral from 0 to 1 of x to the ix dx is the infinite sum from negative I n to the n plus 1, n plus 1. And this is the exact actual value of the integral that we were looking for. Thank you for watching this video, and I hope I see you next video.